So hello, continuation of our lecture in fluid flow measurements. So we discuss now Venturi meter, another device used in measuring uh, discharge through pipes. So Venturi meter, it consists of converging tube which is connected to the main pipe or the inlet and ending in a cylindrical section which is called the throat, and a diverging section which is connected again to the main pipe at the outlet. So uh, here's what Venturi meter looks like. So we have an inlet pipe, then we have the throat. Okay, this portion is your throat. Okay, this is the inlet, and it will end in the outlet. So that's how we measure fluid uh, flow here in this device. So here in Venturi meter, we will just identify 2 points from the inlet pipe. Say this is point A, and a point at the throat, point B. So let's just determine the values for the elevation head. If we will put uh, manometer at the throat and at the inlet and measure the equivalent heads. Say this is, we can use H or we can use Z. So here in Venturi meter, we will just apply Bernoulli equation in order for us to determine the required, especially the flow rate on this pipe. Okay, so again, we will use Bernoulli equation. So later we will answer some sample problems in Venturi meter by just applying Bernoulli equation. So that's why considering those 2 points that I've identified here, so we will just apply Bernoulli energy equation in order for us to determine either the velocities on each point as well as the discharge. Next is the nozzle. The nozzle is a converging tube installed at the end of a pipe or hose for a purpose of increasing the velocity of the issuing jet. So same purpose with orifice. So a nozzle has an opening that has similar characteristic as an orifice. That's why we can apply the same equation in solving the flow rate in a nozzle. So all we need to do is multiply the coefficient of discharge to the area, cross-sectional area of the nozzle, and multiplied by the theoretical velocity, or the square root of 2gh. Next, we have a pitot tube. So pitot tube is a bent L-shaped or U-shaped tube with both ends open and is used to measure the velocity of fluid flow. So it is also used in measuring the airflow, the velocity of airflow, which is usually used in airplane speedometer. So this is pitot tube. It can be in the shape of this one, an L-shaped pitot tube, or a U-shaped pitot tube. So again, here in pitot tube computations, we will also apply Bernoulli's energy equation here by identifying 2 points in the pipe or in the tube, within the tube or within the pipe. Then we'll be able to determine the velocity. Okay. Next, for unsteady flow, the flow through orifice, spheres, or tubes is said to be steady only if the total head producing flow H is constant. The amount of fluid being discharged for a time t can therefore be computed using the formula. So the volume is the product of discharge multiplied by the time. So in some conditions, however, the head over an orifice tube or weir may vary as the fluid flows out, and thus causing the flow to be unsteady. So for unsteady flow, considering this tank right here, which is being supplied by a liquid and simultaneously discharging through an outlet pipe. So we have a discharge, inlet discharge, and the outlet discharge. So in order for us to determine the time required for it to change its head from a certain elevation to another elevation, the delta H, so we can compute that using this equation right here. So we will use integration if its cross or surface area or the cross-sectional area of the container is varying in shape. So here's our equivalent equation where we have an upper and lower limit of h1 and h2. H1 is the initial height of the liquid and h2 is the final height of the liquid. So this is the solution if we have an inlet, if the container is being supplied by liquid and there is an opening where water comes out. Okay, so if there is no water that is being added in the container, so we'll just cancel out. Okay, just cancel out the Q in, and we will have this equation. Okay, just take the absolute value of outlet discharge. Okay, so this is now the solution. Next, okay, so if the surface area of the container is variable, it is varying in shape, so all of the expression here, okay, should be expressed in terms of h, because since our upper and lower limit are in terms of height, so we will find a way to derive or make an equation within this within this solution where we should express it in terms of h. But if the container or the tank is prismatic, so we can easily use this solution right here. Okay, so if the cross section is constant, okay, or the cross sectional area of the container is constant, so this is the derived equation based on the previous solution, where if it is prismatic, we can use this equation: 2as over the coefficient of discharge multiplied by the area of the orifice or the outlet times the square root of 2g, then multiplied by the difference of square root of h1 and square root of h2, or the initial height and the final height. Okay, next, so if the liquid flows through a submerged orifice, here's your orifice or tube connecting two tanks, the time for the head to change from h1 to h2 is, so in this situation, if we have this initial water level or liquid level, then we have an orifice connecting these two tanks. So in order for us to compute the time required for both liquids to reach these points and these dashed lines here, okay, so we have H1 and H2 as the difference in elevation from its original position H1 and the final difference in elevation H2. So the time required for it to reach this level is computed using this equation. Okay, so if we have a varying cross section of the tank, again we can use this general formula where we will integrate. Okay, we express again the equation, the solution in terms of H, but if the container has a uniform cross-sectional area, so we can just simply use this solution right here. So T equals to AS1 AS2 over AS1 plus AS2 multiplied by 2 over the coefficient of discharge, area of orifice, the square root of 2G multiplied by H1 minus H2. Okay, so let's now solve some problems. Example number 1. Oil flows through a pipe as shown in the figure. Determine the discharge of oil in the pipe assuming coefficient of discharge of 0.63. Here's the given figure for the Venturi meter. So let's solve this. We have points 1 and 2. Okay. Given are the diameter of the inlet pipe, which is 250 mm, and we have a 100 mm diameter orifice here at the throat. Then we use mercury in measuring the pressure head at point 1 and point 2. So point 1 it has a pressure head which is lower than point 2, has a difference of 350 mm. So let's compute now the discharge in this pipe. So using Bernoulli's energy equation, so the energy at point 1 is just equals to the energy at point 2. So energy at point 1, sum of velocity head, pressure head, and Z at point 2 velocity head squared to G plus P2 over gamma plus Z2. So the discharge here at point 1 is just the same as the discharge at point 2. Okay, they are equal. Equals to Q2. So we can simply substitute, since the discharge is equals to area times velocity. We have V equals to Q over A. So we substitute now the velocities in terms of Q so that we can directly solve Q in this equation. So for velocity 1, we have Q over area 1 raised to 2 all over 2G plus P1 over gamma plus Z1 equals to Q over A sub 2 squared over 2G plus pressure at point 2 gamma plus Z sub 2. So let's substitute now values. So at point 1, okay, this is Q squared over 2G multiplied by area squared. So area is that's cross section of area 250 mm. So 0.25 meter raised to 2 pi d squared over 4, then we raise it by 2, because that's a1 raised to 2, plus p1 over gamma plus z sub 1, okay, z at point 1 and point 2, they are of the same elevation, so they are same location. Okay, the centroid of the cross section of each point, so they are in line, so they are both 0, so they will just cancel out each other. Q squared, so for point 2 we have 2g, and the area at the orifice 100 mm, so pi 0.1 squared over 4, then we raise it again to 2, plus p2 over gamma. So we solve p1 over gamma minus p2 over gamma, that is equals to q squared over, let's solve this, 2g multiplied by pi over 0.1. Okay, let's solve this denominator right here, where g is 9.81 meter per second squared. So 2 times 9.81 times pi 0.1 squared over 4. Then we raise it again by 2. That's 0.0012. Okay, 0.0012 if that's in the denominator, 0.012, but if we raise it to -1, it will become a numerator. Okay, so this is equivalent to 828.2686 q squared, subtracted by, okay, this is just this value right here. Okay, it is subtracted by, so later this value here is 826.2686 q squared. On the other hand, this one we subtract it by q squared over this value right here, 2g pi 0.25 squared over 4 raised to 2, then raised to -1 to make it numerator. So this is 0.25. Okay, but if we didn't raise it to -1, the answer is 0.047276. Okay, but we raise it to -1, 21. Okay, this is 21.1525 q squared. So let's rewrite the equation. P1 over gamma minus P2 over gamma equals to 826.2686 q squared minus 21.1525 q squared. So the difference in pressure is 805.1161 q squared. Okay, this is equation 1. So the next solution here now is to find this difference in pressure from point 1 and point 2. So Using the same principle as the difference in pressure, which is equals to the sum of the unit weight of the fluid multiplied by H in finding the difference in pressure from point 1 to point 2. What we only need to do is to divide both sides by the unit weight. Therefore, if we're going to sum up the pressure heads from point 1 to point 2, we have P2 over gamma minus P1 over gamma. So the only condition here is that our equivalent heads should be of the same type of fluid. So it means that since we have here mercury, we have to convert the equivalent head of mercury into oil. Okay, so the sum of heads, because our unit weight that will be used here is for the unit weight of oil, same as in equation 1. So P2 over gamma minus P1 over gamma equals to sum of the head from point 1. So point 1 going to this point, that's oil. So that's Z plus 0.35. Then we have mercury. So this height will be cancelled out. So this only remains 0.35 height. That is subtraction because going up. 0.35 in meters. So this is mercury. We convert it to oil by multiplying the specific gravity of mercury, which is 13.6, over unit weight or specific gravity of the oil. Then add the height Z for oil. Z negative going up. This is negative. So it means Z is cancelled out. So P2 over gamma minus P1 over gamma is equals to negative 0.35 times 13.6 over 0.91. Okay, then we add 0.35 because right here we have 0.35. So the total is positive. Sorry, negative. Okay, that's negative 4.881 meters. So we multiply both sides by negative 1. So our equation will now be P1, the negative will become positive, and P2 will become negative, equals to 4.881 meters. So this is equation 2. We can now equate the 2. We substitute P1 over gamma minus P2 over gamma by 4.881 right here. So this is 4.881 meters equals to 805.1161 Q squared. So since we are consistent in unit that we used here, which are in meters and seconds, so our unit for Q will be cubic meter per second. So we divide both sides by 805.1161 1161. So the answer for Q squared is 0.00606, then take the square root. So 4.881 over 805.1161. So the exact value for Q is 0.07786. That's in cubic meters per second. So this is just the theoretical discharge. So it means that we have to compute the actual discharge because we have a given uh, coefficient of discharge. So C times the theoretical discharge. So C is 0.63. 0.63 times 0.07786 cubic meters per second. So the actual discharge in the pipe is 0.63, 0.049053 cubic meters per second, or in liters per second, just multiply 1000. We have 49.053 liters per second. So this is the answer for this problem. Okay. Next example, all discharges from a pipe through a sharp crested round orifice as shown. So the coefficient of contraction Cc and Cv 0.62 and 0.68. Calculate the discharge through the orifice and the diameter and the actual velocity in the jet. Okay, so we are required to determine the discharge on the orifice, the diameter, that's referring to the actual diameter of the orifice, and the actual velocity in the jet. Okay, so first let's determine the theoretical discharge. Okay, which is here. We can determine the theoretical discharge by taking the energy equation at point 1 and point 2. So at point 1 we have velocity head, pressure head, Z, and point 2 velocity head, pressure head, and Z. So Z is both 0, they are the same elevation, point 1 and point 2. So the discharge at point 1 and point 2 are the same. Okay, they are the same because it's flowing on a single direction and there are no other outlet pipe. So this manometer here, this U-shaped manometer here, is just used to measure the pressure, okay, the pressure head at point 1. So again, same solution as of the previous example. We need to express this velocity in terms of Q. So V1 therefore is Q over A, area 1. So let's calculate that, as well as V2, Q over A, so 2. So we can rewrite this as the area is pi d squared over 4. So we have 4Q over pi times the D. At point 1, 0.3 meter diameter is 2. And we have 4Q over pi times the theoretical 75, 0.075 raised to 2. Okay, we substitute that now here. We have Q over 4Q over pi times 0.3 meters. That will be raised to 2 over 2 times G, 9.81 meter per second squared, plus P1 over gamma equals to V2 4Q over pi times 0.075 meter squared and we raise it to 2 over 2 times 9.81 meter per second plus P2 over gamma. So there's no given head loss here. So this equation is enough. Again, P1 over gamma minus P2 over gamma is equals to this term subtracted by this term. So let's evaluate the equivalent coefficient for this term right here. We solve this. That's 4 raised to 2. Okay. 4 over pi 0.075 squared over 2 times 9.2. Okay, 2000. 1611.4167 q squared subtracted by this term. Just change the diameter by 0.3. Okay, 10.2008 q squared. So difference in pressure P1 pressure head P1 over gamma minus P2 over gamma is 2611.4167 minus 10.2008. 2601.2159 squared. This is equation 1. For the equation 2, we take the sum of pressures again from point 1, but we will end at point 3, okay, because the tube is not connected to this orifice. So this is an example of pitot tube, okay. So this is a pitot tube. So it means from point 1 to point 3, okay, point 1 to point 3, we take the sum of its pressure head. So it means from point 3 over gamma minus point 1 over gamma, P pressure at point 1 is equals to, from point 1 going to this interface, we have a height of 0.75 meters. Then subtracted by this height of mercury, okay. So from point 1 going to point 3, this direction. So this is going up, means negative. So 0.18. So since this is mercury, we have to convert it to oil. So this multiplied by specific gravity of mercury over specific gravity of oil, 0.85, which is given. Okay. So the pressure at point 3, so that's an open surface here in this figure. So it means that the pressure at point 3 is 0. Okay. So negative P1 over gamma equals to 0.75 minus 0.18 times 13.6 over 0.85. We have negative 2.13 meters, or positive, because we have negative P1 here. We multiply both sides by negative. So we have P1, which is 2.13. Okay. So how about pressure at point 2? So the pressure at point 2 in the orifice is that it is the opening of this pipe. So we are at the free air surface. Okay, it means that the pressure here at point 2 is 0. So we can now compute the discharge. from this equation 1. So we substitute it now here. We have 2.13 meters equals to 2601.2159 squared. So we divide both sides, point 2159, 2601.2159, then take the square root to find Q. So Q therefore is equals to square root of 2.13 over 2601.2159. So the answer here for Q, the theoretical discharge, is 0.0286 cubic meters per second. Then we have given CC, coefficient of contraction, 0.62, CV 0.98. So we can compute the coefficient of discharge by multiplying CC and CV. 0.62, 0.98 is 0.6076. Then we can now compute the actual discharge by multiplying C to theoretical. 0.6076 times 0.0286 0.0174 cubic meters per second. That's the actual discharge. Or in liters per second, just multiply 1000, 17.4 liters per second. Okay. So the other required are the actual diameter. For the actual diameter, we already have the discharge. Okay. So if we have a theoretical diameter or the diameter of the opening, which is 75 mm, so the actual diameter of the water that is flowing out on this orifice can be computed using the coefficient of contraction. As we recall, the coefficient of contraction is just the area A over the given cross-sectional area. So A here is the actual, just the lowercase a, and the capital letter A is your opening of the orifice. So we can compute that as, so the area, it has a formula of pi d squared over 4. So they have both pi over 4. So what will remain is d, diameter. So d squared over squared. So again, the lowercase d is the diameter of the water, of the liquid, which is oil, and the capital letter D is your opening of the orifice. So we have 0.62 equals to d squared over, okay, so if we want to have a millimeter diameter, we can use millimeter raised to 2. Okay, so d squared equals to 0.62 multiplied by 75 mm raised to 2. So we have a millimeter squared unit, but we will take the square root of that to have a unit of millimeter. So square root of 0.62 times 75 squared. So we have a diameter of 59.055 millimeter. That's the opening, or the diameter of the liquid or of the oil that is flowing out on this orifice. For the actual velocity, we will use the coefficient of velocity. So we can have the actual velocity divided by the theoretical. But since we already have the diameter, actual diameter and the actual discharge, we can also use that. Okay, we can also use that by just dividing the discharge and the cross-sectional area. Or we solve this theoretical velocity here. Okay, so the theoretical velocity can be computed by the theoretical discharge, okay, theoretical discharge divided by the theoretical area or the cross-sectional area of the opening of the pipe. So we can compute that. We have 0.0286 the theoretical discharge divided by cross-sectional area pi times 0.075 squared over 4. So this is your theoretical. 0.0286 over pi times 0.075. Okay, that's 6.474 meter per second. So the actual velocity product of CV and theoretical velocity. CV is 0.98 and 6.474. The answer for the actual velocity is, just multiply this by 0.98. 6.344 meter per second. So this is your answer here. Okay. So here are your final answers. This one for the actual discharge, actual diameter, and the actual velocity. Next problem.